Hi everyone, today I want to introduce you to anti-differentiation using substitution. So for this video, I want to show you a very simple example of how you can use substitution, or simply called substitution, to find an integral, okay? So now the integral that we're going to solve is going to be this one right here. So you have the integral of tangent x dx, okay? This is the bad boy that we have. So now tangent x, of course, is a pretty interesting function because we can rewrite it in terms of another function, okay? So now we know that there is a trigonometric identity that says that tangent will be equal to sine divided by cosine, okay? And you can use that information to rewrite this integral as the integral of sine x over cosine x dx, okay? This is just differential x. You could also write it in the numerator, just if you didn't know that would be the same thing. Remember, you're basically multiplying y. This would actually be y prime, okay? This would be a derivative, and you're multiplying by the differential, okay? So now let's continue with the use substitution problem. So if you want to solve this derivative, there are many ways in which this integral. So there are many ways in which you could do it, but one of the best ways is you could use substitution. So when you use substitution, you want to find a u, and that is going to be an expression in the integrand. The integrand is going to be the function that you have between the integral sign and the differential. So you want to find a u value that its derivative will yield a very close number, or a very close expression to another expression that you have in the integrand, okay? So let me show you something. You could say that, what if we so I'm going to say the following. Let u be equal to cosine x, okay? So now we could rewrite this integral in terms of u, okay? And let me show you how you can do that. If you take the derivative of u and none, I should phrase it like this. If you find the differential of u, that is going to be u prime times dx, well, you can do something really nice to replace dx in this expression. So we have that the differential of u, which is going to be du, is going to be equal to the derivative of cosine, which we know is going to be negative sine x, times the differential of x, okay? Now, there is a very important resemblance that I hope that you can see now. Over here, you have sine x times the differential of x, and over here, you also have sine x times differential of x, okay? So something you can do is the following. You can rewrite this integral as the integral u is going to be equal to cosine x, so you're going to have 1 over u, okay? And now what about sine x times dx? Well, sine x times dx is going to be equal to, so you can move the negative sign to the other side of the equation, so you can just simply multiply, and I'm actually going to continue on this side, now it's down here. So this is going to be minus the differential of u will be equal to sine x times dx, okay? So you have 1 over u, which is 1 over cosine, which is what you have in this expression. And now you can multiply by sine x times dx. And we know sine x times differential of x is going to be the differential of u with a negative coefficient, okay, a -1. So let's do that. So this may not be the best notation, but you could totally do it like this. So negative differential of u, okay? You could do it like this. And this would be the same as the integral with a negative sign on front. Remember, this is a coefficient of -1, so you can move it outside the integral sign. And this would be equal to the integral of 1 over u du, okay? And now it's pretty easy to solve this. You can just see that this will be negative times the natural log of, usually some people write absolute value. I would say you should write absolute value when you use a natural log, because remember, the natural log function is not defined, it's not defined for any negative inputs, so you need to write the absolute value notation. So this would be the negative natural log of u, absolute value, plus, remember, we're going to have a constant c, okay? And remember, I probably didn't mention it explicitly, but I hope that you already know that if you have 1 over u, you cannot use the power rule. Remember, there's an integral power rule that just says that let me do that sign again. So you have that the integral of x to the n with respect to x, or differential x, is going to be equal to x to the n plus 1 over n plus 1. When n is equal to -1, you can see that you would get a division by 0 case, so you can't use this power rule when you have 1 over u or 1 over x. It's the same thing. So you need to use natural log, okay? Because remember, the derivative of ln u or ln x is 1 over u, okay? So this, well, this equation makes sense. And of course, you need to add the constant because when you differentiate, this constant will be lost. And well, you need to mention that there could be any constant c, okay? Hey, I'm sorry, I had to, erase the board for a moment because someone just knocked my door, and I went outside and I talked to them, and then I erased the board. I don't know why, because I should have left what I had before here on the board, but it doesn't matter. So let's continue. So the last thing that I wrote was that the resulting integral was negative integral of 1 over u du, okay? And because you have this would give you an exponent of -1, so you cannot use the power rule, and you need to use natural log. So this would be the same as the natural log of u plus c, okay? Now, you could leave this as your answer, but remember that at the beginning, we said that u was equal to cosine x, okay? This was the substitution that we used. So you can just simply rewrite this result as the natural log of the absolute value of cosine x, okay? And this would be plus c, okay? Now you can differentiate this and you will see that you will get back to our original equation, okay? Our original function, okay? So yeah, that's been the entire thing, and I hope that you learned something. This is a very brief introduction to u substitution. Of course, there are more complicated problems that you can try with substitution, but this is a very simple one, okay? And I thought it was appropriate to begin with something basic. Integration is really cool. I should also say that. I think it's funny. It's funnier and it's better in pretty much every way than differentiation. Differentiation, you just need to apply thousands of rules. Well, not thousands, but yeah, you know what I mean. You need to just apply rules and just apply them over and over again. And I think there's not too much fun, or I would say, yeah, there's not too much fun if you differentiate, but if you integrate, that's better. That's way cooler. And I enjoy recording integration videos way more than differentiation videos. So yeah. So yeah, see you in the following video.